All right, let's go over the exam one practice that's posted for you. The first question is a set of questions about the two graphics. As part of a study on New York air quality in 1973, measurements of ozone in parts per billion were taken from 1 to 3 p.m. at Roosevelt Island for 153 days with 116 days of good data. The average for each of the 116 days is shown in the histogram and box plot below. So take a look at the histogram and box plot, and we want to answer what the distribution of ozone level is. So what shape is it? Remember I said you can look at which way the tail goes. So this one has a long right tail. Another way you can think of it is it looks like the right side of a normal distribution. This one's called skewed right. All right, the mean then is going to be what compared to the median? Well, remember that the mean is the balancing point in the distribution, and it goes in the direction of a skew or outliers. And since our skew is to the right, the mean is going to go higher to balance that distribution. So here, the mean is going to be larger than the median ozone level. If it was a skewed left distribution, the mean would be lower than the median ozone level. All right, thinking about Chebyshev's and the empirical rule, which one is it okay to use for this distribution? Well, remember that the empirical rule only works if you've got a unimodal symmetric data set. Remember, it came from the normal distribution, so your data set distribution needs to look basically like a bell-shaped distribution to use the empirical rule. Chebyshev's works for any shaped distribution. So here, because we have a skewed distribution, the empirical rule is not appropriate to use, but we can always use Chebyshev's. So the answer to this one is Chebyshev's only. All right, when would you choose a box plot over a histogram? Well, remember that a box plot is really good for side-by-side comparisons when you want to break a quantitative data set up into separate groups according to a categorical variable. So here, that's when you want to make side-by-side comparisons. Now, if I flip this question around and ask when would you choose a histogram over a box plot, that's when you want to make sure that you can see intricate shapes, features of the shape of the distribution. Remember, you can see multimodality in a histogram, but you can't see it when you use a box plot. All right, so which graphical display is best for showing change over time? Well, of course, that's the line graph. So a box plot is used for quantitative data sets, medium to large size quantitative data sets. A histogram is for the same situation when you've got a big set of numbers. A line graph shows change over time, and of course a pie graph or pie chart shows all the parts of a whole for a categorical variable. All right, which measure of center can be used for categorical, otherwise known as qualitative data? Well, there are 3 measures of center that we learned, the mean, median, and mode. And the mode is the only one that has the special quality that it works for qualitative data on top of quantitative data. The median and mean only work for quantitative data for a big set of numbers. All right, if an observation is added to the low end of a distribution, so let's picture an outlier that's much lower than the rest of the data, the standard deviation does what? Well, the mean would go in the direction of that outlier, so the mean would decrease, but the standard deviation is a measure of variability. It doesn't care which direction your extreme observations are in. It only cares that you have more variability. It only cares that you have an observation that's really far from the mean. So the standard deviation, when there's more variability, always increases. All right, what's the standard deviation expressed as a percent of the mean? That's the definition of our coefficient of variation. So remember, we have that example where you can picture a distribution that is centered at 1,000,000 and another distribution that's centered at 20. Both of them have a standard deviation of 5. Well, you can imagine, even though that standard deviation is the same, it means something different in a distribution that's centered at 1,000,000 versus one that's centered at 20. And so in a situation like that, you might want to use a normalized version of the standard deviation, the coefficient of variation. It just gives you a relative measure of dispersion. All right, 2 events are said to be disjoint if what? So disjointedness is that kind of physical property that you can picture. That's they share no outcomes in common. They have no intersection. If I asked you to identify the definition of independence, what would it be? Remember, the definition of independence is one that's more theoretical, a little tougher to picture. That's knowledge that one occurs does not affect the probability of the other one occurring. It gives you no additional information. So answer choice D is the definition of independent events. All right, moving right along. So some questions about the probability rules that you learned. Suppose 28, this is actual data from a couple years ago, 28% at that time of University of South Carolina students were on the Dean's List, and 2.7% of students are scholarship athletes. 0.7% of students are on both the Dean's List and a scholarship athlete. So the first question is, for a randomly selected scholarship athlete, what's the probability they're on the Dean's List? Remember, I first recommend taking the English language and writing your probability statement down. So what's the probability that we're looking for here? We're looking for the probability of being on the Dean's List. So that's the probability of being on the Dean's List. But we have some additional information, right? Given that you're a scholarship athlete. So we want the probability of the Dean's List given a scholarship athlete. And we know the definition, we know the formula for computing a conditional probability. That's the probability of their intersection. So the probability of the Dean's List intersect athlete, or and athlete, divided by the probability of the thing you're conditioning on, the probability of being an athlete. And we know that the probability of being in the intersection for that numerator is 0.007, because 0.7% of students are on both the Dean's List and are an athlete. And we know that the probability of being an athlete is 2.7% is 0.027. So we have 0.007 divided by 0.027 for 2.26 or 26%. All right, so make sure you know those probability rules. 11, for a randomly selected student, find the probability of not being on the Dean's List. That's a complement, right? That's the probability of the Dean's List complement. And so you can use your complement rule. That's 1 minus the probability of being on the Dean's List. And we know that 28% of students are on the Dean's List, so that leaves 78% of students who aren't on the Dean's List. 1 minus 0.28 is 0.72, or 72%. All right, what's the probability of a randomly selected University of South Carolina student being a scholarship athlete or on the Dean's List? So this is an or question, so this is one of your addition rules. This is a union that we're trying to compute the probability of. So this is where you're supposed to picture it on a Venn diagram. So we have Dean's List, and we have scholarship athlete, and then we've got people in both. And so we want to compute the union. So we want the size of this whole stuff. So if I add the size of the Dean's List circle to the size of the athlete circle, what have I done? I've double counted everyone in this intersection. Everyone in there got counted twice. So I need to subtract it out once. So the answer here is the probability of being on the Dean's List plus the probability of being an athlete minus the probability of being in both. The table below shows the distribution of the number of visits to the eye doctor for a college student. So suppose that somewhere a student can only visit 0 times, 1 time, or twice during a semester. And they visit 0 times, 75% of students visit 0 times, 15% visit once, and 10% visit twice. How do we compute the expected number of visits to the eye doctor? That's that expected value that we talked about, which is also known as a population mean. So to get the expected value of a discrete random variable, you take each possible value times its probability and add them up. So it's going to be 0 times 0.75 plus 1 times 0.15 plus 2 times 0.10, which is 0.35. Notice that you don't need a calculator because I'm going to do all the calculations out for you in the answer choices. And believe me, it just makes things easier on test day. All right, so a call center receives calls at the rate of 100 per hour. You want to estimate the probability of getting fewer than 50 calls in the next hour. So we need to decide what distribution this is. Well, we're looking at the number of events in an interval. When you're counting the number of events, that's definitely a discrete distribution. So that rules out the normal and the exponential right away. So we're between the binomial and the Poisson. This is the Poisson distribution because we're counting the number of events in an interval. 16, a coin is flipped 20 times and you want to calculate the probability of getting 3 heads out of the 20 flips. Which distribution should you use? Again, we're counting something, the number of heads on coin flips. So it's discrete, it's not any of these continuous distributions. We're not counting the number of events in a certain interval. So here, we're just interested in a number of successes. It's a binomial distribution. All right, for a particular hotel chain, 13% of hotel invoices are paid using American Express. For a random sample of 80 invoices, find the following. The expected number using American Express. This is a binomial setting, and so our expected value in a binomial distribution is n times p. So n here is 80, and because we're looking at 80 invoices, and p is the probability of a success is 0.13. Notice that we have 2 answer choices that have 80 times 0.13. One of them rounds the answer to a whole number, and the other one leaves it as a decimal form. You should not round expected values. Remember, it's a theoretical balancing point in the distribution. If we were to collect many samples of 80 invoices and look at the number that use American Express and average all of those numbers, they would come out in the long run to be 10.4. All right, the probability that 7 use American Express. So this is a binomial situation. You can see that in the answer choices too. And so the first step is to change the English language into a probability statement. So the probability that 7 use American Express is the probability that our binomial random variable equals 7. And when we have an equal sign in that probability statement, we can directly go to the dbinom function with 7 as our number of interest. 19, the probability that less than 7 use American Express. So let's take the English language and write that in a probability statement. That's the probability that that binomial random variable is less than 7. Now, we don't directly have a binomial function in R that does strictly less than, but we do have one that does less than or equal. So if you have less than 7 transactions that used American Express, that's the same thing as less than or equal to 6. So now that we have a less than or equal to sign sitting there, we can use a p-binom function. So that rules out A and B, and we're at C or D. And the probability of being less than or equal to 6 is going to be p-binom of 6. All right. And the probability that more than 8 use American Express, write that in a probability statement. That's more than 8. We don't directly have a binomial function in R that computes strictly greater than. So let's change this into a less than or equal to problem. So the first step that I usually recommend taking is just taking the greater than sign and changing it into a greater than or equal. That way, when you're using the complement rule or subtracting something, you're going to play the same game every time and be less apt to make an error. All right, so if you're bigger than 8, you're bigger than or equal to 9. And if you want to keep 9 on up, then you can do 1 minus 8 on down, because 8 on down is the complement of 9 on up. And everything in the sample space adds to 1. So to look at the probability of being bigger than or equal to 9, it's the same thing as 1 minus the chance of being less than or equal to 8. And now that we have a less than or equal to sitting here, we can use the p-binom function. So it's going to be 1 minus p-binom, my number of interest is 8. Excellent. Oh, let's do one more of these because there's another situation that we can do. Let me just make up a question on the fly. So let's suppose that I asked the probability of being more than 7, but no more than 20. All right, so how do we calculate that? Well, first let's write the English language into a probability statement. So I usually just write my numbers with less than signs around my variable. So, and then I look at the blurb, the prompt, and I ask myself if those should be strict or non-strict inequalities. More than 7, we're good to go on the 7. That's strictly more than 7. But no more than 20 means it could possibly be 20. And so we need to put an or equal to sign here. All right, and the next thing I recommend doing is making sure that both of them are written in terms of an or equal to. So if you're more than 7, you're more than or equal to 8. So now I've changed both of those endpoints into an or equal to probability. And I can use p binom of 20 right? But what does that give me? That gives me 20 on down. But I only want to keep 8 through 20. So if I want to keep 8 through 20, but this p binom gave me 0 through 20, I can just subtract 0 through 7, which is p binom of 7. So think about it. If you want to keep 8 through 20, you can throw away 7 on down. So make sure you know how to do the equal to probabilities, the greater than and greater than or equal, the less than and less than or equal, and being between. So practice, practice, practice. You can use your Connect homework for study attempts to redo your homeworks and make sure that you're getting these correct. And I also have extra practice posted in Canvas. All right, so now we have a set of continuous distribution questions. Your exam is going to have a set of discrete questions, just like the binomial ones we just did, and it's going to have a set of continuous, just like these normal ones that we're going to do now. So make sure you're prepared for those. Research shows that the more timestamps you can put on your brain, the better. And also, you need to test yourself. You can't just read what someone else wrote or watch me do it on the video. You need to print this out and do it yourself. All right, so suppose flight times from Columbia to Atlanta are normally distributed with a mean of 45 minutes and a standard deviation of 5 minutes. Choose the correct R statement to find the probability a flight is more than 37 minutes, but does not last longer than 50 minutes. Now, because this is a continuous distribution, I can write my probability statement, okay? And I can put my strict and non-strict inequalities in there. More than 37, we're good on the lower end, but does not last longer than 50. Technically, this is the probability we're looking for. But since this is a continuous distribution, that or equal to does not matter. Because if you use the d-norm function in a continuous distribution, if you use one of the d functions in R on a continuous distribution, that just gives you the height of the curve at that value. And remember, there are uncountably infinite number of values that this variable can take on. So you can't assign a probability to each value. That's not valid. So you're never going to use the d-norm function for anything other than when you're doing theoretical calculations. It is not interpreted as a probability. So you can't compute the probability that x exactly equals one particular value in the normal or exponential distribution. All right, because of this, we don't have to be as careful as we were when we were doing our discrete distribution calculations. Here, you just always do p norm of your upper number minus p norm of your lower number, which is p norm of 50 minus p norm of 37. All right. 22, choose the correct R statement. Okay, so choose the correct R statement that finds the 95th percentile for flight times. So that's the Q functions. So remember, the P functions do less than or equal. The D functions plug in the X and get you the height of the curve or the height of the histogram bar. And the Q functions take a probability, an area to the left, and they return the value that corresponds to that. So the Q function for the 95th percentile is going to be Q norm of 0.95 because we want the 95th percentile in the distribution that's centered at 45 and has a standard deviation of 5. Notice answer choice D has Q norm of 0.95, but this is not a correct answer because that would be in the special standard normal distribution that's centered at 0 and has a standard deviation of 1. All right, interpret what it means for an observation from this distribution to have a z-score of negative 0.25. This observation is 2.5 standard deviations below average. A z-score washes away your units. It puts it on a scale of standard deviations, and then the minus sign tells you it's below average. All right, and what is the standard normal distribution? The standard normal distribution is the special normal distribution that has mean 0 and standard deviation 1. All distributions in statistics have area 1 under the curve. So it is not the only normal distribution that has area 1 under the curve, and it definitely is used for practical situations. Suppose the number of accidents at malfunction junction follows a Poisson distribution with a rate of 0.75 accidents per day. So those of you who are not from the Columbia area, we do have a malfunction junction. It's the I-2620 interchange. That's its nickname. And I actually found out it's something like, it's way more than 0.75 accidents per day there. I think it's like 3 or something. But anyway, I made up this number when I was doing this example. So what distribution does the time between accidents follow? Well, first let me pose the question, what distribution is the number of accidents per day follow? Well, per day is a time interval, and you're counting the number of accidents, so that is a Poisson distribution. When you're looking at the time between those events in a Poisson distribution, the time between them is an exponential distribution. So this 0.75 is our rate. That's our lambda for our Poisson distribution. And so the expected time between accidents, that's the mean of the exponential, is 1 over lambda, which is 1 over 0.75, which is 1.33 days. Okay. So a statistic, is it the same from sample to sample or different from sample to sample? It definitely varies from sample to sample because a statistic, like a sample mean, is going to be a little bit different from sample to sample because of sampling variability. What's the central limit theorem? That says that the sample mean will have a normal distribution as long as you have a large enough sample size. Those of you who have had a previous statistics course might recognize B. That's the law of large numbers. All right, the average ticket or average bill, average receipt at a restaurant is $45.75 with a standard deviation of $7. Find the probability that the average of 4 customers' tickets will be less than $50. Now, the key here is we need to know the distribution of the sample mean because we want the probability that the sample mean of 4 customers' tickets is going to be less than $50, right? So we need to know the distribution of the sample mean. Well, the sample mean has a normal distribution under 2 conditions. One is if these receipts have a normal distribution, these tickets have a normal distribution, then you're guaranteed that the sample mean has a normal distribution, or if you have a large enough sample size, which is generally considered greater than 30 or 40. Then your central limit theorem kicks in and gives you a normal distribution. Here, you are not told that these average tickets have a normal distribution, and you also only have a sample size of 4, so you can't compute the probability from the information given. However, in question 30, we're looking at the same probability. We want the probability that the average of 50 customers' bills is less than $50. We weren't told that the average ticket, that the tickets have a normal distribution, so we can't guarantee that the X bar has a normal distribution that way, but we do have a large sample size. We have a sample size of 50. So we can assume that the central limit theorem is going to kick in and give us a normal distribution for our sample mean. And we told you that the sample mean is a normal distribution as long as you have a large enough sample size, and it's centered at mu, the mean of the original distribution of the x's, but it has less variability as you increase the sample size. That sample mean is going to vary less from sample to sample with a bigger sample size. How much less? By a factor of the square root of the sample size. So we're going to want P norm of our number of interest 50 in the distribution that's centered at $45.75 with a standard deviation of sigma 7 divided by the square root of the sample size 50. All right, so we learned that if the sample mean has a normal distribution, as long as you have a large enough sample size, we can standardize that and do x bar minus mu over sigma divided by the square root of n. And that thing had what distribution? That had a z distribution. That had a normal distribution centered at 0 with a standard deviation of 1. But what happens when you plug s in instead of sigma? It's not quite a standard normal distribution. That has what we call a t distribution. We're going to use that with our confidence intervals and our hypothesis tests a bunch this semester. All right, if you're doing a study to determine sample size and you come out with recommending your n is 151.2, the rule is that because you were solving for an inequality, you need to round up. You can't have 0.2 of a person, so you need to round up to the next whole number of 152. All right, how do you reduce the variability in the sample proportion? How do you reduce the variability in general in statistics? Get a bigger sample size. So increasing the sample size is going to reduce the variability. 34, using a larger sample size will do what? Well, that decreases variability, so that's going to generally decrease the width of a confidence interval. And 35, using a larger confidence level will do what? But when you increase the confidence level, that's like, think about getting a fish out of an aquarium. If you want to be more confident that you're going to catch that fish, you need a bigger net. So when you increase the confidence level, you're going to increase the width of the interval. This is part of the reason why we settle on 95% confidence. Think about it. If 95% confidence means that only 95% of our confidence intervals using that method, if we were to get many samples, are going to actually be telling the truth, they're going to actually contain the true parameter, that means we're wrong 5% of the time, which is kind of a lot. So why don't we just use 99.9% confidence? Because that increases the width of the interval, and sometimes it would make it too wide to be useful. So we try to strike that balance. All right, that's it. Good luck studying for your test, and send me messages in Canvas if you've got questions.